Howdy, welcome to the short course, Introduction to Containers. I am your host, Richard Lawrence. Today, we will be learning about containers. In particular, we'll be learning about the container named Singularity. And the first thing we're going to do is practice doing some basic tasks with containers. And then later today, we'll practice doing some advanced tasks with containers. So after you take this course, you should be able to decide if containers are right for you. Containers are a way to make some workflows simpler. In particular, if you are collaborating with people at other institutions, then containers may be right for you. And if that's the case, then you need to know how to go about doing that, getting started with that. So in addition to this course, we have a number of resources that you can use to learn containers. The first is our wiki here. Our wiki is a knowledge base. This page was written by me. It contains many of the same things that you'll learn today in this short course. So if you need to come back later, that's one place you can go to get the information you need. Likewise, we post video recordings of our short courses like this one on our YouTube channel. So if you need to hear me say it again, that's one way you can go about doing that. Of course, Singularity has its own manual, as does Docker, which is closely related. And if you find that there's something I did not teach very well, then maybe you want a different short course. So here we have some links to some other short courses. And I'll show you these links again later, so you don't have to write them down or anything. Next, getting started, what even is containers? Containers are a way to make applications more portable. And so what I mean by that is you have let's say you have a developer, and the developer is working on their own personal machine. So that would be their personal machine. So they just start installing things they need. And then eventually they build an application. And after they're done developing all of that, they would like to share what they've done. So they need to be able to bundle up the work that they did and send it to you, for example. One way to do that would be to take literally everything that's on their personal computer and replicate it on the host computer. So that would be called the virtual machine. So the hardware, obviously, you can't bundle up and put that in a file, but everything that is considered a file, starting with the operating system, you would bundle all of that up and send it in a large file, and then that would land on the host computer. So the host computer, with its own operating system, would therefore need to have a way to interact with the guest operating system. So that would be called the virtual machine manager. The virtual machine strategy can handle pretty much any type of application, but there's a huge cost, which is that the operating system itself is a very large amount of data and even a significant amount of compute power to run. And so when you see that on the guest machine, the host machine has now 2 operating systems running on it. That is redundant. So a lot of memory and computing power are being wasted. If you wanted to do this more efficiently, where we don't replicate the operating system, but we just keep the parts of the developer's work that are specific to their application, not the operating system itself, then what you would have done is you would have created a container. A container is the minimum of the bundle of files that is needed to run that application, which excludes the operating system and excludes as many of the libraries that you believe will reasonably be present on the target machine to be running the container. And then in that case, you need a way for the host operating system to communicate with the container. And so then you have the container runtime, which will be installed on that machine. So containers are theoretically not a new technology. They have been around for over a decade now. The first containers being native Linux development called LXC, but they didn't really take off in popularity until Docker. Docker in 2013 is the first really successful container runtime. And one of the reasons it's successful is because it's easy to use. You install Docker, and because it's so powerful, it can do everything for you. But Docker has some disadvantages that we'll get into, and so more evolution was needed. Here are some more recent container runtimes. Singularity in 2015, Charlie Cloud 2017, Podman 2018. So these ones were developed to try to overcome the weaknesses that are in the Docker Singularity runtime. So what's in a container? So the container has two parts. You have the image, which is a file that bundles up all of the parts of an environment, the libraries and the applications that are needed in order to make that application portable. Images are generally built by experts. Often the same people who develop the application will also build a container. And you can find the images in online repositories because they're meant for sharing. And so this is the same thing I showed you on the other page, which corresponds to the rectangle around those few items here. And then the next part of the container is the runtime, which is the thing you install on your local machine in order to interact with the container. The runtime acts as a compatibility layer between the container environment and the host operating system. Now, the runtime can moderate between different operating systems, but it cannot operate between different architectures. So there is at least a minimum amount of compatibility between an image and a operating system, which is that they have to be developed on the same architecture. But once that architecture has been defined, then the operating system can be relatively free on top of that. Why do we use containers? So I've already kind of hinted at this. Containers are shareable. You can upload an image to a public repository on the internet, and then other people can download it and run your application on their machine. So that's an easy sharing method. And containers are portable, which means provided that you and your friend are using the same architecture, you don't have to be using the same operating system or the same libraries. So one container image can apply to many different machines. And finally, reproducibility, because containers allow two people to execute the exact same applications. Then if they need to verify that the other has done the work correctly, you can verify it yourself. You don't need to walk over to their machine in order to do it. Now, I have told you that there were some problems with Docker, and then the other container runtimes developed in order to address those problems. Here at Texas A&M, the container runtime that we're currently using is named Singularity. And So I will tell you how that one works. Recently, Singularity changed its name. It became Apptainer. This is because it joined the Linux open source community. It used to be private, but I will continue to refer to it as Singularity because what we have installed on our clusters calls itself Singularity, because it's still that's what the executable is in the installation. So at some point in the future, we may have to start saying Apptainer, but for today, we're going to continue to say Singularity. Singularity is a container runtime, but it can read and convert the Docker images. So if you find an image repository that's full of Docker container images, then you can port those onto a Singularity-based runtime system pretty easily. Singularity natively knows how to do that. And that's so people who are developing containers in Docker can still share their containers with people who are running containers using Singularity. Now, Singularity has a few more features that are specific to Singularity. The file system inside the container is isolated, which means that when you go to read and write files inside the container environment, you don't see the files in the host operating system environment, so you can make sure you're not getting confused which file is which. Next, the user inside the container is the same as the user outside. So this means that if you have permission to do the thing, or if you don't have permission to do the thing, then using Singularity doesn't change that. So Singularity doesn't add any security concerns due to using Singularity. Then the security concern is of importance because Singularity containers are meant to be used on clusters, that is, shared computing environments with multiple users. Docker is meant to be used on a singular user environment where one user has control of the machine. So the requirement that we have to share our machines with multiple users means that there are some limitations that Singularity must accept. But the trade-off of that is, since Singularity is specifically designed for high-performance computing clusters, they also get to optimize in a few different ways. So Singularity runs close to the hardware, meaning it knows how to communicate directly with the high-performance resources that we have, and therefore Singularity containers tend to run fast, usually about the same speed as if you had installed the software yourself. So I mentioned that the user inside and the user outside is related to security. So that's important. Singularity addresses security concerns about Docker using that feature and other features. So the first is privileges. Since the user inside and the user outside are the same user, Singularity grants the user no additional privileges or permissions, so you can't harm the cluster by using Singularity, nor can other users harm you. And independence is a feature because when you don't have control of your machine because you're sharing it with other users, then you should be able to do your tasks without having to ask the administrators for root permissions just to do your tasks. So Singularity allows you to do your container tasks without being a root user yourself. Here at HPRC at Texas A&M, there are some concerns due to our resources in particular. So the Singularity activities are computing intense. So therefore, we don't allow users to do them on the login nodes. The login nodes are shared at any time. Multiple users may be using a login node. So if one user wanted to do some computing intense activities, then it wouldn't be fair to the other users who then wouldn't be able to use the login node. So whenever you wish to do Singularity activities, you have to get a compute node, and I'll show you how to do that during our exercises. Next, Singularity image files. You recognize them because they end in the extension .sif, which is short for the Singularity image file. They're flat. That means they don't share data with any other image files. If you're used to a different container runtime, such as Docker, Docker containers are layered. So that means if two containers are very similar, the part that they have in common will only be stored once on disk. Singularity image files are flat, which means if you have multiple images, then the total file usage is the sum of each of them. The advantage of doing this is if you need to distribute a file onto multiple machines, it's easy to do. It's just a copy operation for one file. The downside is they are quite large on disk, so you should be putting them in your Scratch space where you have enough space, you have enough quota to handle something as large as an image, and not in your home directory. So next up, we're going to be doing some exercises. You're going to learn how to do basic container activities. In order to learn how to do these things, you need to be logged into our cluster. So you can use your favorite method. You can use your SSH client, or you can use the portal. Either is fine. I will spend a moment and show you what either of those look like before we get started on our exercises, so you have a chance to catch up. So let's say you start from our own webpage, hprc.tamu.edu. Over here, the menu called Portal will allow you to log into one of our clusters. So for today, we'll be using the Grace cluster. That's the newer of these two clusters. So if you want to log into the Grace cluster, of course, you'll need to use your same NetID and two-factor authentication that you would use for any of the Texas A&M system services. In my case, I have the Duo set up on my phone, so when I click the button, then I get a little notification. And that allows you to log into our portal. If you're not familiar with the portal, I'll take a moment to remind you how it looks like. So up at the top here, you have a file navigator that you can use to interact with your files. You may feel that today you want to do that. We have a job menu that allows you to submit batch jobs. You won't need to submit a batch job today. We have the cluster menu that allows you to get a terminal. You will need a terminal to do some of today's exercises, so this may be the way that you choose to get a terminal. Interactive apps allows you to launch a variety of graphical applications. We will do a couple of examples later on today. I consider them to be kind of optional, but also really cool. I hope you choose to do that. And then we have a dashboard that will show you your quota. Make sure you have enough space on Scratch. Make sure you have enough compute time to do today's exercises. So for our first exercises, we'll be using the command line. So we need to go to the cluster menu and use the shell access option to get a command line. So this command line will land on a login node, which means we won't be able to do our Singularity activities on the login node, but I will show you how to get to a compute node from a login node during our exercises. So if you are using SSH to get to a login node, then you might open a terminal on your local machine and do something like SSH grace.hprc.tamu.edu. Instructions. We have instructions for these things on our wiki. Let's go take a look at our wiki. So if you started from our homepage, then you would see on the left panel, we have user guides. And one of the user guides is for Grace. It is in fact a page on our wiki. So there is an access page in this group of pages that discusses how to get access to Grace from the command line. So for example, here in this first section, it discusses how to use SSH. The syntax would look like that. And then there are some notes about how many login nodes there are, some notes about how to get started with two-factor authentication. So this is where you go if you got confused. Now, while you are catching up and getting your terminal, I will resume talking about the containers. So the first task that we will need to do is we will need to get a container image. Container images live in repositories. They're created by experts. So we need to know where the repositories are and how to use them. So the most common repository is named Docker Hub. Docker Hub is a free-to-use platform where anybody can create images and share them. Of course, the images are in the Docker container file format. There are other repositories. The Singularity repositories are generally not as useful because people who don't typically develop specifically for Singularity. They may develop for multiple container runtimes, in which case you would want a more broadly applicable repository. NVIDIA, for example, has their own repository where they build containers with really high quality software inside. Quay.io is a repository that is similar to Docker Hub, but has more features for developers. So if you see something on Quay, it's probably more serious than something on Docker. Biocontainers is a specific subset of Quay.io that's got a family of curated biology applications. And these are listed on our wiki in the Singularity section of our wiki. Why don't we take a moment to look at that? So here is our wiki again. This is the Singularity page. And you'll see it has a lot of similar things as to what's going on in this short course, how to build images, how to get images from repositories. So if you forget what the repositories are or how to use them, that's where you would go to get help. Okay, so let's take a closer look at Docker Hub. This is what Docker Hub looks like. I went and grabbed a screenshot. So every page of Docker Hub is in the form of a group, an individual or a group of people or an organization, followed by a slash, followed by the name of the image. So the name of the image is usually named after the software that's in the image, but not always. And this is similar to how GitHub works. if you're familiar with GitHub. And Docker Hub also has a default group, which is the underscore. So if that happens to be the group that published your image, which we'll see one example, then you simply omit that part from the name of the image. So here's an example on the right where the TensorFlow organization, that is the developers of the TensorFlow software, have built an image that contains the TensorFlow software. And so the name of the organization and the name of the image are both TensorFlow. TensorFlow is an AI framework for Python, for those of you who are into that. Now, once you have located an image repository, you will notice that the images come have been tagged with similar to version numbers. So you need to select a version number that you want your image to be. If you do not select an image version, then you will get something at random, which may or may not be what you wanted. And so for that reason, I recommend that you always manually select a version. So in the case of the Docker Hub, these versions are called tags. So you can click over to the tag tab and search the tags for the information you're looking for. So in the case of this TensorFlow repository, you may wish to have a TensorFlow that is compatible with the Jupyter IDE. We'll see an example of that later. And you may also wish for the container to be compatible with an NVIDIA GPU. So then in this case, you would search for a tag involving those words, and you'll see that the results here tell you why, yes, there is such a tag, and this is how you would use it if you were using the Docker runtime. But we are not using the Docker runtime, we're using the Singularity runtime. So you want to take the information that you see here, and we're going to modify it a little bit to use with the Singularity. So on the previous page, it suggests you would use the Docker pull command, but we are actually going to use the Singularity pull command, which is not exactly the same. There are a few differences. So when you use Singularity to pull an image from Docker Hub or another repository, it can convert that into the Singularity image file format automatically at the same time. In that case, you would specify which file format you want by including the file extension in the target file name where you wish the image to land. So the syntax looks like Singularity pull target file name, including the extension. So for example, we might use the .sif extension to let Singularity know, please convert this to a Singularity image file. And then source refers to the location on the internet where the image can be found. And that is related to what we saw on the Docker Hub tags page. For the specific example that we saw on that other page, the argument for the Docker images is going to contain that group and name and tag that Docker suggested we use. So we go and double check how that looks like. That is TensorFlow, latest GPU Jupyter. And then specifically for the Singularity pull command, you have to prepend all of that with Docker : / to let Singularity know that we are pulling from Docker Hub. And here this backslash in the yellow just means this is meant to be written all on one line, but I couldn't fit it all in one line in this slide, so that's what that means. Now, this slide says that we are going to be pulling we're going to be doing a job on a compute node. So we need to get access to a compute node. And this is how we get access to compute nodes if you happen to start from a login node. So we use the srun command to get access to a compute node from a login node. And then you have to enter some really basic batch commands. Hopefully you are familiar with how these batch arguments works. In order to get any job running on HPRC, you have to specify at minimum a memory and a wall time. And because srun does not take a batch file as its argument, but instead a command, then the command we're going to use here is bash, which says I want to get a terminal on a compute node. So that's what that means. There's some other things here that are just related to how that terminal is going to function. And then let's go ahead and get started. I will walk through how to do that on my terminal. So this is where we left off. We had our portal that we logged into, and then we went to the cluster and got a terminal on the cluster. So now I'm going to execute the srun command to get my terminal onto a login node. Srun space, we have to define a memory, --mem equals, and you can put, for example, something like, I don't know, 1000 megabytes. So you want 1 gigabyte of memory. Oops, looks like I have a typo. And then you need to specify a wall time. So --time equals 1 hour, 0 minutes, 0 seconds. You do have to specify the minutes and the seconds, or else it will think you're asking for minutes or seconds. And then because we're going to be setting up a terminal, we have to use the --sudo terminal flag. Then we give the name of our terminal, which is bash, and the I to tell bash that we're going to be interacting rather than running a specific bash command. So you hit enter and then you wait. If at any time you're trying to get a job to start, for example, using the srun command, if you happen to see an error that looks like socket timeout, it just means that Slurm was very busy at that moment and you need to try again. After 2 or 3 tries, it should work normally. Now you'll see that my prompt has changed. It used to say Grace1, and now it says C321. So Grace1 is one of our login nodes, and C321 is one of our compute nodes. The compute nodes do have Singularity installed, so let's check that that's the case. Which Singularity? Yep, there it is. So you should get this far and get yourself a terminal on a compute node in order to do today's exercises. Please take a moment to catch up. In the meantime, I will review the containers. So once we're on a compute node, there were a couple of other notes about using Singularity from our compute nodes. I previously mentioned that Singularity files are large on disk, so you want to put them in Scratch, not in your home directory. Now, Singularity by default will use a cache in your home directory while it's doing its work. It's possible if the file you're downloading is so large that it will overflow this cache, you'll run out of quota in home and not be able to complete the operation. So I recommend that you tell Singularity to use a cache in your Scratch directory instead. So the way to do that is to set this environment variable. And in Bash, the way you set any environment variable is with the export command. So export Singularity cache dir equals, and then anywhere in your Scratch area. I like Scratch / dot singularity. Dot means it will be invisible, so it won't bother you. Let's go ahead and set that up. Export Singularity cache dir equals Scratch / dot singularity. Oops, more typos. So the $ Scratch is just a variable that points to the location of your Scratch directory. And then the last thing is that the compute nodes do not have direct access to the internet. But since the pulling from the internet is literally what we're doing, we need to get access to the internet by method of a proxy. So we have a web proxy module to set that up for you. So just module load web proxy. And now your terminal, if you have completed these steps, is ready to do a Singularity pull command and get a container. I suppose that means we should choose a directory for the container to go. So why not navigate to your Scratch directory if you wish to put the container in your Scratch directory. And then maybe make a directory to put it in. Something like that. So wherever your current directory is that would be an easy way to put your container images where you want them to go. But that's optional. The container we're going to download first is small enough to fit in your home directory. So if you're struggling to catch up, you can skip that step. Now would be a good time to pause and make sure people have caught up. So if you are caught up to where you have a terminal on a compute node, then you should respond on Zoom. So the first image that we're going to download for our exercise is the hello world image. Of course, in any language, the first program you want to write is hello world. So with containers, the first image is going to be the hello world container image. It happens to be hosted on Docker Hub with the _, the default organization. So we're going to be pulling that. Now I've replicated here the srun command in case it turns out that you need it again. I'll have it on all the pages where you need it. And then, so the new command for this slide starts down here with Singularity pull hello world.sif. So go ahead and take a minute to execute these commands. The commands we've already talked about: srun, exporting the cache dir, which I recommend, module load web proxy, which is necessary, and then the syntax looks like Singularity pull, the name of the file. So in this case, we'll name it hello world.sif, the extension .sif lets Singularity know what image format you want to save this in. And then the \, of course, here means this is meant to be written all in one line. I just ran out of space on my slide. And then we use the Docker syntax, docker : // and then the name of the image on Docker Hub. But since the _ group is default, we just omit it. So then it's just hello world. And we don't need a tag because, there's only one version of hello world anyway. Let me go ahead and do that exercise. Singularity pull hello world.sif Docker :/ hello, what was it? Hello world with a a hyphen. Is that what it looked like? Yes. And then you will hit enter. So Singularity says, I went to the internet, I found something, I downloaded it, I made an image file. All right, let's see if there's an image file. ls hello world.sif. Indeed, it exists. So then I have successfully completed this Singularity poll exercise. I'm going to talk for a moment. This is not an exercise. Let's say that you wanted to pull an image file and it's just a bit on the large side and it's going to take a really long time. This does happen. In that case, you don't want to be doing it interactively because then you have to sit there and, tap on your desk while you're bored. So that's why we have batch files. So this is an example of a batch file that you might use to pull an image without doing it interactively. So we would just start composing a pretty ordinary looking batch file. We have here some batch parameters, a job name, a wall time, some number of tasks, some amount of memory. And then for the commands, just replicate what we already have done. Go into your Scratch directory, setting your cache dir, which is even more important if it's going to be a large image file. Module load web proxy, and then your Singularity pull command. Then you would submit this job using sbatch or the portal's job menu, and then the file would be downloaded in the background at your leisure. We don't have to do this exercise today, but I wanted you to know, at least be aware of how you might do it. So in addition to downloading images from online repositories, we do provide a small number of pre-built images at this location on disk. And I would like you to take a look at this time because we'll be using these for the rest of our exercises. So if you forget where these are, you can also read about it in our wiki. So if I click there, it says the images are on disk at this location. And here's a short list of some images that are there. And so we're going to investigate that by navigating to that location and seeing the images ourselves. I am now back in my terminal, and we're going to investigate those pre-built images. Scratch group, is that right? No, Scratch data Singularity images. That's the file path that we need to investigate. Let's see what's there. There are a number of files here, and we're going to be using many of these for the later examples today. So you can stay in this directory for the time being once you have found it. Scratch data Singularity images. Now we will move on to what can we do with containers once we have an image file. There are several things you need to be able to know how to do, and so we'll do some exercises. So when you wish to use a container image, there are 3 methods with Singularity that you can use a container image. You can do it interactively, which means get a shell inside the container. You can execute specific commands in the container, or the container itself can sometimes be treated as an executable, in which case we have a run command. And I'll show you examples of all 3 of these. So the first one we're going to do is we're going to try that run command. We have a hello world.sif, which is on disk, and we're going to execute it using Singularity Run hello world.sif. We're also going to execute it using the // syntax that any executable might have. So the hello world.sif is not here, which means I need to go back to where I was before. Singularity run hello world. Oops. All right. So there were a lot of words that came out of this one, including hello from Docker. That was the one we wanted to see. We wanted to see hello from Docker. A bunch of other words came out as well. Those are not important. So we could do the same thing by typing / hello world.sif. It outputs the same text. And that is pretty much all that the hello world image can do. It can print out this text, including hello from Docker, just to show that it worked. It's a very minimal image. It doesn't have any other features that it can do. It can't even do a shell. I used the CD- shortcut to go back and forth between the current directory and the previous directory. You didn't have to do the hello world exercise if you didn't feel like it, but we'll do a more important exercise next. So after the Singularity run, let's try getting a shell inside a container environment. So for this purpose, again, you need to be on a compute node. So if you happen to have lost your compute node, then you can get back to it with srun. How do you know? Well, if the name of the machine on the left of the $sign is login or Grace, then that would be a login node. Whereas if it says, you know, a letter and some numbers, that would be a compute node. So for this example, we're going to use the Fedora HPRC lab image. The .img format is from an older version of Singularity, but it still works. And so the command is Singularity shell, name of the image file, and that will give you a new prompt. The prompt will change. It will say Singularity to show you that now your environment is different. So let's give that a try. Singularity shell, the Fedora, and I use tab autocomplete because tab autocomplete is your friend. Fedora is an operating system of Linux that is used for desktop computers. And now I have a Singularity shell prompt. So I'm going to try some basic activities. It suggests that we ask what our own username is to confirm that it is in fact the same as it was before, and that we check out the etc. OS release file, which for any Linux operating system will contain some information about the operating system. So who am I? I should be the same user as I was before. Yes, I am. And let's check out the etc. OS release file that says that this is a Fedora operating system. Okay, and I feel like I have done enough activities inside the shell for the moment, so I'm going to use exit to leave the shell. Now I'm back on my compute node outside of the container. And why don't I try that etc. OS release trick on the compute node? Aha! The compute node here is not Fedora, it's actually CentOS. So in the container, there was evidence that it was a Fedora operating system, and outside the container, there's evidence that it was a CentOS operating system. I'm slightly misspeaking here because, as I told you, there is only one real physical operating system. What's happening is just a handful of libraries are present in the container that are exactly the difference between CentOS and Fedora. So everything that would be like in common to all Linux operating systems is not replicated in the container. Only things that are specific to Fedora, including the etc. OS release file. So the next example we're going to do is we're going to try to execute a specific command in the container, but not interactively. That is to say, we type the commands that will be executed, and we don't type them in a Singularity shell prompt. So in that case, we want to use the Singularity Exec command, which allows you to execute specific commands inside a container environment. So the syntax is Singularity Exec, the name of the container image, followed by whatever commands you wish to run. So for this example, I would like to execute some Python commands. So I might say, Python 3, please tell me your version. Python 3, please print hello from Python. So let me try out these examples. So make sure you're still on a compute node. If you have dropped off of your compute node, here's the S run again to remind you how it looks like. And the syntax here, I will go ahead and try it out. Singularity Exec Fedora, which does contain a Python installation. So tab autocomplete is your friend. And if you're not familiar with Python, no big deal. You don't have to use Python specifically. You could execute your favorite bash command instead. So Singularity Exec from the Fedora image, I'm going to do Python version. It says Python 2.7, but Python 3 version, Python 3.6.6. So inside this container, there are two Pythons installed. One is named Python, one is named Python 3. And of course, Python can also interpret Python commands. Sorry, lots of typos. Oh dear, lots of typos. Yeah, that's my bad. I did a typo. There we go. So the Python inside the container executed that Python command. Next, I will talk about working with files. So I previously told you that the file system inside the container is isolated from the file system outside the container. And we saw an example of that with the etc. OS release file. The OS release file in the container belonged to the Fedora library, and which was completely distinct from the etc. OS release file that was on the real physical compute node. But what if you do want to have access to files that are on the real physical compute node? Then you will have to make sure that that directory is mounted. So here at HPRC, by default, Singularity will mount your home directory. It will mount the current directory if it can. And I believe it will also mount a few other things that you may discover. If you wish to mount specific other directories, you can use the Singularity bind path environment variable or the bind command line option. So let's take a look at an example of that. Let's suppose that you wish to create a file in the container and have that file exist in the real physical file system, perhaps in your Scratch directory. Then you would use the Singularity. For example, let's suppose I wanted to do this task interactively. Then I would use the Singularity shell with the bind argument, --bind, and then you type in a comma-separated list of directories that you would like to be mapped into your container. So you might wish the Scratch directory to be mapped in the container, and therefore all of the subdirectories of Scratch, which would include your Scratch directory. And then finally, of course, as always, the name of an image file. So then you can do your activities. Touch is the command in Bash for to just create an empty file so we can see that it exists. And then we will verify that it does still exist after leaving the container. So let's say I wished to do Singularity shell and then add the bind command. So I would like to bind Scratch so that I know that my Scratch directory will be present inside the container as well as outside the container. And I'll use the same Fedora image that we've already seen. And then I get a shell terminal. So I might, for example, decide that I want to create a file in my Scratch directory in that intro to containers directory that we already created, that I already created. What did I name that thing again? Can't quite remember. Intro containers Spring 22. Test file. We'll just name it test file. And then if I was to exit the command, exit the container, now I'm back on my compute node, and let's verify if that file actually made it into the real Scratch directory. Yes, it did. So that file now exists in my real Scratch directory, even though when I created it, I was working in a container, which we know has a distinct isolated file system. And the bind command made that, the bind argument made that possible. So in this case, I actually used the environment variable $Scratch in my example. $Scratch is defined on the regular compute node. And because Singularity is not specifically told to override that, it will just allow it to continue to exist inside the container. Containers can override your environment variables, so you should watch out though. Here's an example. We're not going to do this one live, but let me just show you. Suppose you wished to do a task like this one in a batch file. Well, here's how you might do it. You might use the Singularity bind path variant, where instead of putting the argument on one line, we're going to put it over here. Export Singularity bind path equals comma separated list of directories that you would like to be present in the container. And then all of the Singularity commands that follow in your batch script will have that property. So here we have two Singularity commands. We have a Singularity Run and we have a Singularity Exec. And both of them will have that bind path active. So we have completed the basic steps of using containers. We will now move on to the advanced slides in a few minutes. But first, I would like to take another look at our wiki to remind you what's there. So, oh. So let's suppose that you go home later and you wanted to take another look at those batch examples. Where can you do that? So on our wiki, hprc.tamu.org, edu/wiki. If you say find the Singularity page by searching software Singularity, then you'll find here a lot of the things we're talking about today. How to get a container image, how to interact with a container. So here's those same pull examples. And here's an example, the one that I showed you already, on how to do a Singularity bind path inside a job script. So that's how you would do that. You would go to our wiki, you would search for Singularity, and you would scroll down to find the same information that we're covering here today. So if you forget the exact syntax, you can always recover it. Not a big deal. And now it is time to move on to some advanced topics. If you are just getting started with containers and you are at this point and you realize that maybe containers are for you, but I haven't really shown you how to do anything useful in a container. So I'm going to try to show you several different examples of something you might do that would be more useful so that you can begin to see how containers might apply to your specific research. I'm going to show you some examples, and I'm also going to show you, I'm going to tell you how to build containers, although you won't be doing that today. Here's our same list of learning resources that I showed you earlier. And the first example that we're going to cover is how to use Singularity with a GPU. So Singularity, as I told you, runs close to the hardware. It knows how to interface with high performance technology, including graphics processing units. So here at HPRC, we have NVIDIA graphics cards. And therefore, Singularity will allow you to use them in your applications. Two requirements. First of all, the container has to have been built using a version of CUDA that is compatible with our graphics cards. So on Grace, that means you need CUDA 11 in the container. It is the responsibility of the container developer to ensure that that is the case. And the next, you just add the --NV, short for NVIDIA, flag to your Singularity command to let Singularity know to do the work of setting it up. Many repositories on Docker Hub do have GPU-ready images. So earlier I showed you an example. TensorFlow has a GPU-ready image. You'll just look for the word GPU in the tag might be, for example, one way that you could find it. And then another place you can get GPU-ready images is directly from NVIDIA themselves. So NVIDIA has a repository, and there are examples of how to pull from that on our wiki. So for today, we will use the TensorFlow example. This TensorFlow came from Docker. It is the Docker TensorFlow 2.41-GPU image, which I have already downloaded and therefore is located in that same directory, Scratch Data Singularity Images. Also in that same location, I wrote a little Python script, tf-gpu-test.py. The purpose of the Python script is just to see whether the GPUs are in fact working correctly. Now, you could, in theory, use that with any TensorFlow, but today we're going to do it in a container because we're not sure if container is capable of interfacing with a GPU. So the first thing we're going to need to do is get access to a GPU, which means we need to leave our current compute node if we're still on one, and get a new compute node that has a GPU. Now, if it turns out that during class you have a hard time getting a GPU, it's not a big deal. You can always try these exercises at home later. I hope most of you can get a GPU at least at some point today. I'm going to try these exercises and hopefully they work for you as you follow along. We do have a limited number of GPUs and sometimes sometimes they're busy. So the first thing to do is the srun command, but this time we're going to add two arguments. The GRES GPU1 flag, which says I need one GPU, please, any type. And the partition equals GPU flag to let Slurm know that you don't want to wait in line behind all the regular jobs. You want to wait in the very short line with just the GPU jobs. So let me get my terminal and I will start on that. So over here, returning to my terminal, you can see that I'm currently on a compute node, but this compute node does not have a GPU. So I need to do exit to get out of my compute node before I do srun and then start those srun arguments. I need memory, some amount of memory, doesn't really matter. I need some amount of time, hopefully enough. I need a GPU, please. Any type will do. And I don't want to wait in line behind the regular jobs. I want to just skip them and go directly to waiting in line behind the people who wanted a GPU. And then finally, I would like a terminal, please. pty bash -hi. It says I have a typo. Ah, yes, I see the typo. I was supposed to put an equal sign here instead of a colon. Typos will get everyone, even me. All right, now let's take a look. It says it queued my job and gave me the node, and here we go. Now my prompt has changed to G006. So I landed on one of our compute nodes that should have an A100 graphics card. We will find out soon enough. Let's return to our slideshow. So once we get access to a compute node that has a GPU, we'll be doing Singularity Exec, and then we'll be using the TensorFlow.sif image file, and then we'll be executing using Python, because this is a Python script, Python 3 tfgpu test.py, and the key new technique for this exercise is the --nv flag. So let me get back my terminal and let's try it. Oops, I don't seem to be in the correct directory. I will have to change directory to scratch data Singularity images, and then I can execute the example command. So I need Singularity exec --nv. We need the TensorFlow image and ends in SIF, right? And then we need to execute the Python 3 tfgpu test.py. If you're confused how I type so fast, of course, it's because I'm using tab autocomplete. Tab autocomplete is your friend. So now I'll hit enter and we'll see what happens. TensorFlow is not the fastest bit of code, and it needs to load the CUDA libraries, which is also not the fastest bit of code, but it does work after a moment. So let's take a look at this output. If you're familiar with CUDA, then this will be something you may have seen before. Otherwise, we'll just skip over it. CUDA detected that there was an A100 graphics card, which is what I told you there would be. And then my script in Python counted how many graphics cards, and it counted that there was one. So that means that inside the container, TensorFlow and CUDA were able to access an A100 graphics card that is on the real physical compute node. So that is very cool. Now, the next thing we're going to do is we're going to immediately leave the compute node, because whenever you're using a graphics card, you're being charged for a pretty good amount of service units. So we don't want to burn up all your service units just doing these little examples. So please do remember to close your GPU jobs when you're not using them. So I did exit, and now I'm back on the login node again. So to review, we learned how to use the --NV flag to let Singularity interface with the local graphics card. Now, some error that can occur is if you can't find tfgpu test.py, you may have to bind the directory that it's in. That can happen to some people. Now, this is not the only way to get access to a graphics card. You can also get access to a graphics card by using our portal. So far today, we've just used the command line. But what good would containers be really if you had to do everything on the command line? We are migrating one at a time all of the container applications onto the portal. And the first one that we're going to show you today is the Jupyter Notebook. So let's go back over to where that portal was. Here we go. So back on the Grace portal, now instead of the cluster menu, if I use the interactive apps menu and scroll all the way down to where it says Jupyter Notebook, you will see that there's a pretty complex form. The form allows you to input what type of environment your Jupyter Notebook should be running in. And today we're going to be picking the container environment so that our Jupyter Notebook will launch in a container. And that will give us access to whatever software is in the container. So you need a path to a Singularity image file. And we are going to be using a Singularity image file that's already available on disk. So let's see the example. So the image file is going to be TensorFlow 241 GPU Jupyter.sif, which is from the same repository as the other image file, except this one has the word Jupyter in it because Jupyter Notebook is installed in the container, which is a requirement for this procedure to work. Now we're going to put that path into the path to Singularity image file box here in this form after we select the container type of environment. And finally, you will also need to select that you want a GPU for your node type if you're going to do this test. Type in the path to Singularity image file. Once again, scratch data Singularity images, TensorFlow 241 GPU Jupyter.sif. There are a couple of apostrophes in, let's say hyphens in there. I suggest that someone put that little snippet into the Zoom chat in case anybody is wanting to follow along, which I do highly recommend. So then we need to scroll down and make sure that we select one of the GPU types in our node type if you want to test whether GPUs actually are available in the. So any would give you a compute node that does not have a GPU. So let's pick a 100, which is the type of GPU we have the most of. Click launch. And you'll get a card that says your session is starting, please wait. It will take about a minute. Okay, my Jupyter session is ready. So I click connect to Jupyter. And then to get a notebook, I come over here and click on new notebook Python 3. And this gives you the Jupyter IDE for Python. An IDE is different than the command line. Instead of executing commands one at a time, you can, edit a file, save the file, and execute multiple commands. So for example, here are the commands that I copied out of the tfgpu test Python script that we already used. So if I execute these, it should give us a similar looking output. CUDA having multiple lines and then saying there's one GPU available. In this case, we didn't get the multiple lines of CUDA. Those probably went to a different file somewhere, but it did find the GPU as we anticipated. So I guess I'll just make this a little bit bigger on my screen and leave it there in case people are wanting to follow along. And hold on for a second while people catch up. And don't forget to hop on back over here to your interactive sessions page and delete your session whenever you're done using it, because jobs that run on GPUs tend to eat up quite a lot of service units. We don't want to eat all your service units, so you can go ahead and end your GPU job whenever you're done using it. Oh, somehow messed up my font size. Okay. Let's continue with the next example. The next example case that we're going to do is Singularity with MPI. Now, MPI is itself a whole nother class. If you're the kind of person that wants to do MPI development, I'm not the person to help you. But in terms of just running an MPI executable, I can maybe help you with that. So the point of containers is that somebody else does the development work, but not everyone will do their development work in the same way. Now, for MPI specifically, there are at least 3 different ways to handle MPI in a container. You can install MPI in the container and then run MPI in the container. This has the advantage of the developer has control over what they're doing, but it has the disadvantage that the MPI is not aware of your specific hardware. You can also install MPI and run MPI outside the container. The advantage is that the MPI is installed by your administrators, so it knows about your local hardware. But the disadvantage is it may have a hard time. The features in the container may not be available because the features in the container don't necessarily know what kind of MPI is outside the container. And then you have that really tricky one where you install MPI outside the container and then run MPI in the container. In that case, you have the additional step of you have to find the MPI that's installed on your local real physical hardware inside the container, which probably involves binding some directories. But if you manage to do all of that, then you have potentially the fastest MPI with the most features. But all of this, whichever one you choose, is going to depend on how the developer of the container intended their container to be used. So you will have to find out before you proceed. Here's an example. We're going to do a simpler example where we're going to run MPI that is installed in the container. So it's going to be easy. It's not going to necessarily be the fastest, but it will work. So here's an example. LAMPS is a chemistry science program. Words are hard. That simulates molecules, many molecules, and it has the capacity to run in parallel using MPI. And I have acquired a container that has a build of LAMPS that can do this, and that's located in our same area. Scratch data Singularity images. The image file is LAMPS stable 29 October. There's a bunch of more words. .saf. So you're going to use tab autocomplete. You're going to start typing LAMPS and then hit tab and get to the point where you have SIF, and that's when you know you're done hitting tab.
And then lamps, because it's a simulation, needs some kind of input to tell you what to simulate. So we have the lamps test input.txt to tell lamps what to simulate. That's in the same location. Now, next, in order to use MPI, you have to have access to multiple cores on the compute node so that you can distribute your task over multiple cores. That's the point of MPI. But that means we have to request multiple cores, which so far we haven't done that today. So we'll have to review. srun is how you get a compute node. This time we're going to add some flags. We're going to add tasks equals 4, nodes equals 1. Both of those matter. Tasks equals 4 tells Slurm that you need 4 cores. And nodes equals 1 means I want all the cores to be on the same node. This particular container with lamps does not know how to access cores that are on multiple nodes. In theory, you could build a container to do that. This just isn't that container. So we're going to have to make sure all our cores are on the same node so lamps can find them. And then you have your usual looking arguments to get a shell on a compute node. So let me go ahead and do that. Okay, what do we have here? We have a login node. Perfect. I want to be on a login node so that I can get on a compute node again. srun tasks is n tasks equals 4 -- nodes equals 1, and then some ordinary looking memory, and then some ordinary looking wall time. And then we do want to be doing interactive things, so it's pty-i. So now I am on compute node 322, and Slurm has given me access to 4 cores. So if I start up any MPI tasks, they should be able to find 4 different cores to live on. Let's go to that scratch data Singularity images folder and check and see if lamps is there. So we have a lamps stable, we have a lamps test input, and a lamps test.slurm. I'm not using the slurm at the moment. So in order to write the lamps log file, you would need to work in a directory that you have permission to do. So it's possible you want to copy some of these things into your Scratch space so that lamps can write its log file. So copy, of course, you would use the cp command to copy a file. I don't need to because I have permission to write in this directory. So I'm just going to execute directly in this directory. So if I remove the log.lamps, lamps will make a new one. So let's talk about how to execute MPI with this lamps. We're going to use Singularity Run, and the reason we're using Singularity Run is this particular container was meant to be run as an executable, such that you provide what the task to be done is as an argument to the executable. It's a bit funny because it kind of looks like what we're doing here is typing in a command. So we should be using Singularity Exec. This is one of those cases where the person who builds the container gets to decide how you do things. So we're using Singularity Run. We're going to bind a working directory. Lamps expects there to be a working directory. Again, that's something specific to this container. But /work doesn't exist on this compute node, so we're going to have to find somewhere to become the /work. So the syntax is bind, and then tempdir is a place that you're allowed to write to. So if we bind that to work, then lamps will believe that work is a thing that exists. And then we continue with the name of the image file, and then finally an MPI command. So in this case, we're going to use MPI run -np4. So we want to use 4 processes, so each one can land on a separate core. And then the executable that MPI is going to launch 4 of is the bin lmp underscore MPI executable, which again, tab autocomplete will not help you in this case because that file doesn't exist on the compute node at the time you're typing this command. And then you provide an input file -in space lamps test input, and that one does exist on the compute node. So let me see if I can get all of that into my command line in one try. Singularity run bind tempdir :/work lamps stable blah blah blah, and then we need the MPI run -np4, and then we need the /lmp bin lmp underscore MPI. Oh dear, more typos. And then finally in the lamps input file, lamps test input, which autocomplete does help with because that is a file that exists on the local disk for the real compute node. Let's see if all of that works. All right, so there's a lot of lamps that we don't necessarily know what it does, but we can look in here and we see that it had 4 MPI tasks, and those 4 tasks were able to use 74% of the total computing power. And up here we can see there's a 2x2 MPI processor grid, which is a total of 4 MPI processes. So even though we don't necessarily know what was going on with the actual simulation, we do see some evidence that MPI did in fact create 4 processes, and those did in fact do more work than a single process could have done, because 74% of 4 cores is a lot more than 1 core. In fact, that's roughly about 3 cores worth of compute power. So there you go. There's your evidence. I'm going to go ahead and someone should probably go ahead and copy that command into the Zoom chat, since it is such a long one, in case anybody's following along and wants to try it themselves. So the next exercise that we're going to do is an example of a biology application. We previously did a chemistry application, and before that AI. So I'm really trying to show you a variety of different kinds of research application. So this bio container comes from Quay.io, which is one of the other repositories that's not Docker Hub. But the syntax is going to be similar because Quay.io has a Docker file format for its images. So this image is named bcbio / nextgen 128.sif, and that's living in the same directory, scratch data singularity images. For this one, you don't need any particular amount of resources on the compute node. So if you have a compute node already, you can just keep it. If you don't have one, you get the same srun syntax here, just to remind you how that works. And then we're going to do Singularity Exec and just look for some things that I happen to know were in the container. So there happens to be a file named bcbio underscore nextgen.py, and it is findable on the command line. So if we ask it, hey, what do you do? Then maybe it will be able to tell us what it does. Another thing you could do is you could launch Python in the container and see if Python is able to import the PySam module. PySam is a It has to do with sequencing DNA, I believe. So if that's available in Python, that certainly is going to be evidence that this container has something. So let me go ahead and try the exercise. I am still on this compute node, so I'll just stay on the compute node. Let's type it in. We need Singularity Exec BCBIO. That's the name of the image. Hit tab autocomplete. That's your friend. And then the command I want to run is bcbio underscore nextgen.py help. I want to ask that script what it can do. Let's see if it exists. Let's see if it knows what it can do. Yeah, it does exist. And it says it has to do with sequencing analysis. It has a lot of arguments. We're not going to play with that for now. Let's try the other thing. Let's see if we can import PySam into Python. So import PySam semicolon print PySam dot underscore version. This is just a little Python snippet. That's one thing you can do if you want to know if a module exists, what version it is. So yes, PySam is findable by Python, and this is its version. I don't know what that means in particular, but it's evidence that the bio container does in fact make it very easy to get access to this particular Python module. I didn't have to install that Python module on the local computer. It's right there in the container. Let's go back to the slide here, and I'll leave that on the screen for a moment in case anybody's wanting to try this exercise. We'll pause here for a moment. Otherwise, it is time to move on to the next topic. We have just one more exercise to do today, which is not specific to an application, but just a different way to do something with containers. So previously we have seen that if you want to write a file to the real physical file system, that you can do that with the bind command. But what happens when you want to add a file to the container, not the real physical file system? So for example, some containers make millions of files. There's nothing you can do about it. You're not the one who wrote the application. But here at HPRC, you have a file quota. So you can't just go around creating millions of files willy-nilly. Then you're going to have a place to put all those files. Well, if this was Docker, you wouldn't have to worry about it because Docker containers are read and write. As you execute a Docker container, you can also change it. You can add to the image file. But Singularity images, because of the requirement that they be operating on shared clusters, have fewer privileges. And so Singularity images by default, most of them are not writable. You cannot change the Singularity image while you're executing it. And if you try to save a file in the container's file system, you'll find that as soon as you stop running, that file no longer exists because the container file system is ephemeral. It is not persistent between runs. So the solution is we create a second file called an overlay. The purpose of the overlay is to be user writable. So I will show you how to do that. Now, in Linux, generically, we have tools that make file systems. So DD writes ones and zeros to a file, and makeFS organizes that into a file system. But the version of makeFS that we would need to work with Singularity is not present on Terra or Grace. But no problem. Containers to the rescue. we have a container that does have the correct version of makefs and a script that knows how to use it. So those are on disk at the same location. We'll take a look at those in a moment. If you were on your personal machine doing Singularity tasks, then you might have the correct version of makefs, or you could choose to install it. In that case, Singularity can do the process of creating an overlay file automatically with the Singularity overlay command. We can't do that on Grace, so we have this alternative. So let's create an overlay file. So here's an exercise. Once again, we need to be on a compute node. If you're already on a compute node, you can just keep using the one you have. And we're going to be using the Ubuntu 18.04 container image, which has the correct version of makefs for this exercise. We're going to be using the overlay example.sh script, which is the thing that knows how to make the overlay file. Those are both located in the same directory where the other things are located. Okay, and then so the syntax for this exercise is very simple. Singularity exec, the name of the image file, and then bash overlay example.sh. It is a bash script, so we use bash to execute it. And let's go ahead and give it a try. So let's see what's here. Yes, there is an Ubuntu. So we're going to go Singularity exec Ubuntu, and then we're going to do bash overlay example.sh. And it says, okay, did some nonsense. If you want to know what that means, you will have to read about it because makefs is a bit on the complicated side. But the result is it put a file here. So there's an overlay file. Let's see if it exists. Yep, it exists. So this example created an overlay file, put it at that location. So that is in the temp space, which is specific to this node. So if you want to keep it, you have to copy it to Scratch. Let's say I do want to keep it. I'll just copy that file over to my Scratch space. Scratch intro containers. Yep, there we go. So now I have a copy of that overlay file in my Scratch space if I want to use it later. For now, I don't think it's going to make a big difference because we're just doing one small exercise. The next part of the exercise is, what if we wanted to use the overlay file? Here's the syntax for using an overlay file. So you add the overlay argument to your Singularity command. So Singularity -- overlay, and then the path to the overlay file, and you put that in your Singularity command. So here's a pretty normal looking Singularity command. Singularity shell, any container. It doesn't have to be the Ubuntu container, but I'll just use it because it's there. Singularity shell -- overlay, path to my overlay, the name of the image file, and then you go ahead and have fun creating some files and directories and see what happens. Okay, so Singularity shell -- overlay, pasting that same path to my overlay, Ubuntu container, and then we get a Singularity terminal, and now we can create some files and directories. So let's make a directory named new directory, and then let's create a file in there like that. So then, of course, if we exit the container, there is no such directory on the real physical file system. That would be nonsense. But if we repeat the Singularity shell command with the overlay flag, so I hit up arrow to cycle through my previous commands, then you can see that, in fact, it is still present in the overlay file system in the container, because the point of that is exactly the point of the overlay file system. It allows you to store files in the container that are not in the real physical file system, in case that matters for quota reasons, for example. And then you hit exit again when we're done with your shell. And that concludes our final exercise for the day. Which means if you're still on a compute node and you feel that you don't need a compute node anymore, then you would type exit to get back on the login node so you don't burn up any service units that you don't need to. So we'll put this back on the screen in case anybody's catching up. Maybe go back to the previous slide for a moment. Go forward again. And then we'll proceed to the last topic of the day, which is something that I'm just going to talk about, and we're not going to do any exercises. So building your own containers, which is an overview with no exercises. We've already seen that Singularity has a .sif image format, but there is another image format called a sandbox, which is a writable directory structure. Singularity build is the command that can convert from one file format to the other. This is mainly useful for modifying images, such as installing new software. If you have an image that's almost what you need, but not quite, you just need to install one more little bit of software. Singularity build might be what you would use to do that. However, since installing software usually requires root privileges, like sudo apt-get, for example, then you would need to do that on your personal machine, because all the Singularity tasks, including Singularity build, you are the same user on the inside as you are on the outside. So Singularity does not give you permission to do sudo apt-get. So if you need to do a sudo apt-get or something like that, then you'll be doing your Singularity build on your personal machine. What would that look like? Well, if you were doing this, which we're not going to, then what you would do is you would start out with an image and you would convert it to a sandbox by doing Singularity build sandbox, and then name the sandbox whatever you wanted to name it. And that would create a directory structure that functions as a container image. And then whenever you want to make changes to it, you would do Singularity shell with the writable flag on and use your sandbox as the image. And if you're planning to install software, then you would go ahead and do sudo so that you would be the root user in the container. And then whenever you're done installing the software, you can convert that sandbox into a final flat image file using Singularity build again, but instead of the sandbox argument, you would simply provide the name of the file ending in .sif. And so that would create a read-only file suitable for use on the cluster, provided that you did these tasks on a machine where you can successfully do the tasks. We can't do these tasks on HPRC because we don't give sudo to everyone. Like we don't even give sudo to most of our own staff. Is dangerous. So what if you didn't want to build a container yourself? What if you're like, this is a container that a robot should build? Well, Singularity has recipes. So Docker has something called a Docker file, which is a recipe for how to build a Docker image. And Singularity has something similar called a recipe, where you can describe how you would build the image. We're not going to go into how to do it, but the recipe could, for example, start from an existing image, install some software, give it a run script so that the container would be an executable, and then Singularity build can assemble all of that together at once, so you don't have to do it on the shell method where you type those commands one at a time. Singularity can execute them all at once. And once you have a recipe file, then Singularity Hub, which I'm not sure if it still exists because Singularity did get converted to Apptainer, but back in the day, you could automatically build containers from recipes on the internet and then download them to your local machine whenever they're ready. I'm not sure if that service is still active, so we're just going to skip right on past this. In case it turns out it's no longer active, we don't want to waste your time on it. So if you have questions about how to build, unfortunately, I won't be able to answer them right now because we can't really do building tasks on HPRC, but I might be able to help you build something at a later time. So how do you get help at a later time? We'll cover that on a slide very soon from now. For now, let's do a conclusion. What have we learned today? We have learned that you should be running containers on the cluster because it's easy. I just type in a few lines and I get access to all kinds of software that experts created. I didn't create it, I didn't install it, it's just available. So here at HPRC, we use the Singularity runtime to execute the containers. We can convert from the Docker file format, which is the most popular file format out there. And we're also developing support for Charlie Cloud, which is a different container runtime. Charlie Cloud will be available in the future. It's not currently available, but keep your eye out for that because Charlie Cloud has even more features than Singularity has. And you should ask for help if you need help. One thing you can ask for is, if only we supported more container tasks on our portal. So far we support the Jupyter task, but there are lots of other container tasks you might do. So you should be letting us know if you feel like you need some of that. I may send a survey. If you do see a survey, I hope you fill it out because those are, they personally matter to me. And then you can ask your questions, although I may not be here right now because I have obviously, other things I need to do, but there should be someone around to answer the basic questions for now. And when you need my help specifically, you can contact me. You can look at our learning resources where I put the information we've already seen on our wiki, on YouTube, and you can send me an email. So all of us staff at HPRC get the emails that you send to help at HPRC. So if you send an email that says, I'm trying to do XYZ and the other thing in containers, then someone will look at it and go, we need Richard to answer this question about containers. So they'll make sure that I take a look at the email, and that's how you get your questions answered. I hope you have an excellent day, and thank you for participating in the short course. If you're in person, you might see pizza in the room. Otherwise, you're going to have to feed yourself. Have a Good Friday.